So we left off at example 4 of our differentiation rules notes. We found our first tangent line using a shortcut rule. So let's look at example 5. So when we have these really convenient shortcut rules that are going to help us to find derivatives quickly, that means we're going to be asked to use them often. But we got to make sure that we are using them appropriately, right? With great power comes great responsibility, a wise uncle once said. And so in example 5, we've got kind of our first, one of our first situations where it's going to be really tempting to use them out of the bounds of where we can use them. So we've got h of x equals, in parentheses, 4x squared plus 1 and times the binomial 2x minus 5. All right, they want us to find h prime of x, so they want us to find the derivative. It might be really tempting to say, well, I can take what's in the first parentheses, I can do my power rule there and get 8x. And I can look at 2x minus 5 and use my power rule there and get 2, multiply those together and get 16x. But it's not how the power rule works. We can't use it on just pieces of our function if those pieces aren't whole terms themselves, right? If our function isn't in a standard form where we got one term plus or minus another term plus or minus another term, we've got a product here. So we got to recognize this as a product and say, hey, we don't have a product rule for derivatives yet. We're about to. So what I can do is I can multiply these polynomials out. All right, I can use some algebra and I can use my FOIL or my box or double distribute, whatever works for you, and multiply these out to get our original function, which is equal to 8x cubed minus 20x squared plus 2x minus 5, right? If you FOIL that out. Now that is in a form where we've got standard form where we've got one term plus or minus another term plus or minus and so on. So there we can use our power rule on each of those terms. So 8x cubed, take the derivative, becomes 24x squared, minus 20x squared, take the derivative, becomes negative 40x. Derivative of 2x is 2, and the derivative of negative 5 is 0. We don't have to write that. Okay, so we can multiply those out and then use our one at a time derivative rules. Example 6, the volume of a cube excuse me, with sides of length s is given by the formula v equals s cubed. Find dv ds when s equals 4 centimeters. Okay, so we've talked a little bit about using functions that are named something that's appropriate to an application, right? With our basketball, highest world record basketball shot, we looked at position being s. This is a different S. This is a side length S. And V is our volume. But it's really common to use variables that make sense in application problems. So we're going to have to make sure that we can transfer our derivative rules, make sure we line up our variables appropriately with our X's and Y's going forward. Okay, so when we see that dv ds, it's the same thing as ddx of V or dy dx. So our v is our y, our s is our x. So you can rewrite it like that if you'd like. Just make sure that you reinterpret it in the end in context of the appropriate units or variables. Okay, so this is the same thing as x cubed. Take the derivative, plug in 4 for our side, which they ask us to do here. So we should get 48 cubic centimeters. That is the units of volume. Okay, we're not cubing 40 cubic centimeters per centimeter. All right, since we're taking that derivative, we get a rate. Okay, we've already seen that the derivative of the sum of two functions is the sum of the derivatives of the two functions. This does not work for the product or quotient of two functions. All right, like we just showed up here in example 5. It doesn't work for the product. 16x, not the same as this trinomial there. To illustrate this, here's another illustration. All right, as if we needed another one. You guys can try this one on your own. Try to take the derivative of x squared and the derivative of 3x, multiply them together. See if you get the same thing as multiplying them together first and then taking the derivative. You'll get something different. All right, so now let's look at a product rule. We do have a product rule. It's just not straightforward. Take the derivative of each factor. All right, so it says if u and v are differentiable functions of x, then the derivative of u times v is u times dv dx plus v times du dx. All right, Soups over there says first d last plus last d first. This is a great little heuristic reminder of what the product rule says. All right, we've got the product of two terms. We can take derivative of the first times derivative of the second plus the second times derivative of the first. Okay, so example A. Let's look at this one together, and then you guys can try example B. Excuse me. So it says y equals, and then we've got two sets of parentheses. So there's our two terms. That's going to be our u, 3 plus 2 root x. And then our v is going to be 5x cubed minus 7. Do you have to label them like that? No, you don't. But you need to be able to identify the first piece and the second piece. All right, so let's use our power rule. Again, you could multiply this all out like we did in example 5 and then take the derivative of each term. Or we can use our power rule. So we can say, all right, first 3 plus 2 root x times the derivative of the second piece. Okay, derivative of 5x cubed is 15x squared. All right, minus 7, that's derivative of 0. All right, so that is our u times dv dx. All right, plus, all right, product rule has a plus in it, plus the second piece, so 5x cubed minus 7 times the derivative of the first. Okay, so go through your process, take the derivative of the first term, should come out to be x to the negative 1/2. All right, so at that point, you need to simplify some. I would distribute your terms through, see if you have any like terms. In this case, we have a x to the 5/2. It's helpful when you're multiplying powers by radicals to convert everything to powers. So that square root of x, make sure you convert it to a 1/2. And then your final answer, you can leave those fraction exponents, or you can convert them back into radicals. You can leave your negative exponents, or you can make them positive. I'm okay either way. Okay, so do the same thing with part B. Try part B on your own. Check your answer with what we've got here. All right, it says a note. It is also valid to multiply out the function first and then take the derivative. We just talked about that. All right, quotient rule. Let's see how we're doing on time. 2 minutes. Cool. Right, u and v are differentiable functions of x. Then d dx of u over v equals v times du dx minus u times dv dx. That looks a lot like the power rule, but it's different in a couple places. Over v squared. All right, so one way to help remember this one is to think about your u and your v, your numerator and your denominator, as high and low, just because it's simple to do that. And then over on the right, we've got low d high minus high d low over low, or low squared. All right, so that's what this translates to. This is a great way to remember this, even though it's goofy. Don't be too proud to recite that in your head or out loud while you're doing these quotient rule problems. All right, so example 9 says we got f of x equals x over x squared plus 1. Okay, so identify you got a quotient. We need to use the quotient rule. So now let's say our u or our high is x, our v or our low, our denominator is x squared plus 1. Then let's use our rule. So this one, we start off, instead of u times dv, we've got v times du for that first term. Okay, so low d high, minus, instead of plus, minus, and then the product of u and dv, okay, or high d low. All that is over low squared, okay, or low times low. All right, denominator times itself. All right, and then it's a process of simplifying, doing algebra, simplifying, seeing if there's anything you can cross out. If not, just do it like I just. Part B, try that one on your own. and check it with what we've got